Okay, so welcome back. Um, I was seeing Anna. Yeah, oh, the story of the friend, the Mountain Dew. Oh, yeah. So quick version of it is Mountain Dew ran this promotion my freshman year of undergrad, which was the only year I lived in the dorms because I was conned into I went to University of Tennessee, and they had tricked us into thinking that we had to live on campus for the first year, which was not true. So we immediately, got off campus as soon as possible. But anyway, in my first year living in the dorm, uh, Mountain Dew had this promotion at the time, which was basically you accrued dew points, and the dew points were accrued in the following way. If you purchased a 12 pack on the inside, there was a voucher code for like three dew points, I think. And then if you bought a 2 liter underneath the cap, there was a voucher code for 1 point. And so they had various things you could cash in the points for. So I can't remember absolutely everything, but like for 350 dew points, you could get a dew hoodie. For 500 dew points, you could get a Mountain Dew themed Xbox with a year of Xbox Live subscription. Also, for 500, you could get a Dew mini fridge. And anyway, uh, also while I was an undergrad, I had a meal plan that included bonus bucks and meal equivalency, so that like if I think I got like 2 guaranteed meals or whatever, but I could turn those meals into bonus bucks if I wanted to. So both me and my roommate basically converted almost every meal we could into bonus bucks, which was just enough to buy a 12 pack, twice a day, basically. And we went through so much Mountain Dew that we joked that, at least in bonus bucks equivalent and the amount of money we spent on it, that we paid more in Dew than we did for our tuition. And we accrued enough Dew points to get 2 hoodies, Xbox Live with a year of Xbox Live or a Mountain Dew Xbox with a year of Xbox Live subscription. We didn't get the mini fridge, but we got a bunch of the other smaller things. So we had like thousands of Dew points. It was pretty good. There's actually a picture of me somewhere floating around, like lying in a giant pile of Mountain Dew cans in my freshman dorm. So anyway, so that was the story I was referring to. So last time I had mentioned that we're approaching like the meat of the course, where we're starting to do Calc 1 or Calc 1 type stuff on functions of more than one variable. So maybe I thought I'd do one more example of sketching one of these functions. So consider the function we talked about this last time, but we didn't sketch it. So if I have a function f of xy that is square root of 4 minus x squared minus y squared, and the question that we answered about this function last time was its maximal domain. Right, so its domain that I am going to start calling R. I'm going to start referring to the domain as R because this is how we're going to refer to it in chapter 14 stuff. So the domain of this f is the set R, which is the set of all xy in R2, such that I'll write it here. X squared plus y squared is less than or equal to 4. Right. We found last time, this was the maximal domain of this function. And of course, this is the closed disk of radius 2. So a better way of characterizing R is just calling it the closed disk of radius 2. And of course, we obtain this just by saying that what is underneath the radical must be greater than or equal to 0. So that's where I get this inequality. And so we know what the domain of this thing looks like. Okay, so now I want to see what the graph of this thing would look like. So I'm going to do what we did last time, which is I consider looking at cross sections, and the cross sections I look at are convenient cross sections made by intersecting the graph of this thing, which I don't know what it looks like now, but I want to intersect it with some easy planes. Okay, so what does the cross section look like if I consider cross section formed by the plane, let's say the YZ plane. Right, so this is the YZ plane. So what does it look like when I intersect the YZ plane with the graph of this function in space? Well, remember, the YZ plane is given by this equation, x is equal to 0, right? It's the set of all x, y, z in space such that x is equal to 0. Okay, Anna, the range, we don't care about the range in a sense. I mean, you know, for us, like, technically, like, the graph that we're going to be drawing is the range, but, you know, like, or the graph will indicate the range. But the reason we don't worry too much about the range is because range is kind of hard to find in general for a lot of functions. So, so we're not going to be worried about the range of the function. Okay. So YZ plane is denoted by the equation x is equal to 0. So then in the YZ plane, f of xy is really f of 0y, which is square root of 4 minus y squared. Now, as we saw last time, right, another way of characterizing this is f of xy determines my z value. So it's totally equivalent to write that this is z is equal to square root of 4 minus y squared. Well, what does the graph of this look like? So in my YZ plane, right, here's y, here's z. What does square root of 4 minus y squared look like? Now, whenever you see square root applied in this way, I'll call this analytically, meaning that whenever you have a square root and the things that you're wanting to do with that square root involve calculus, right? What do I mean, right? So if I'm solving a quadratic equation, and in the process of solving this quadratic equation, I need to take the square root of 4. If I ask you what the square root of 4 is, you're going to tell me plus and minus 2, right? Because a number in general has 2 square roots. And that's fine. And that, I would call that an algebraic operation, okay? So if I'm asking you to solve a quadratic, then when you take a square root, you got to remember there's 2 square roots of a number typically, right? But if the thing that we're going to do involves calculus, then when we have a square root here, we always assume that it's the positive one. And of course, the reason we do that is so that the thing we're dealing with is actually a function. What's the graph of z equals square root of 4 minus y squared look like? It is the upper semicircle of radius 2, right? All right, so here's minus 2, here's 2. This is what z equals square root of 4 minus y squared looks like. This is the upper semicircle of radius 2. If you wanted the lower semicircle, there'd be a minus sign here. Okay. All right, so that's what this thing looks like in the YZ plane. What about in the XZ plane? So it's going to be a similar story. In the XZ plane, that's where y is equal to 0. And in the XZ plane, f of xy is f of x0, which is square root of 4 minus x squared. And so in the XZ plane, this looks like the following. It looks exactly the same, except this is the XZ plane, not the YZ plane. Now, I know what you're going to say. You're going to say, well, can't we do an example of where it looks like something in one direction and something else in another direction? Yeah, sure. I'll do one of those examples here in a second. Okay, to show you what this thing looks like. Okay, so anyway, so in the YZ plane and XZ plane, it looks like this. Okay, so that gives me some idea of what some cross sections look like. But let's consider the other types of cross sections we considered last time, which were cross sections where I'm cutting through with a plane that is parallel to the XY plane. So let's just start with the XY plane. In the last example we did, the XY plane didn't help us that much because it only intersected the graph at a single point. Okay, and so let's consider the XY plane. So in the xy plane, that of course is the equation z is equal to 0. Z here, of course, is our functional value. So this is since z is equal to f of xy, what this means is that my cross-section for the xy plane is given by f of xy is equal to 0. Right? But f of xy is square root of 4 minus x squared minus y squared. So that's equal to 0, which means that squaring both sides, 4 minus x squared minus y squared is equal to 0. So that x squared plus y squared is equal to 4. What is that? What curve is that? This is the circle of radius 2, centered at the origin of the xy plane. So in the xy plane, I get the full circle of radius 2. Okay. Now again, we've basically nailed down what this thing looks like, but let's make sure that we really understand what's going on. Let's look at the intersection of this plane that is parallel to the xy plane. Say z is equal to 1. So what about when z is equal to 1? When z is equal to 1, we expect, since f is relatively nice here, to get an example of what we talked about last time, which is a level curve, right? So level curves in general, level curves are of the form f of xy is equal to c, where this f function is nice enough. Okay, so this is what level curves are. And if you recall, my example of level curves, I gave this example of a topographical map of some mountainous region, right, where the level curves are just intersections, right? They are the cross sections of intersecting a plane with that terrain, right? And the plane is at some height, so it is parallel to the xy plane, or sea level in the case of a topographical map. Okay, and so f of xy is equal to 1. What does this mean? This means that square root of 4 minus x squared minus y squared is equal to 1, so that 4 minus x squared minus y squared is equal to 1. Right, squaring both sides, so that x squared plus y squared is equal to 3. What is that? This is circle of radius root 3. Okay. And quickly, if we choose different values of c here, if we look at different level curves here, eventually, of course, this is going to be undefined because eventually, as I increase this, I am going to get a plane that doesn't intersect the graph of this function. If you don't believe me, right, then you can just check, like, what is f of x, y is equal to, say, 5. What about this level curve? What would I get? I would get square root of 4 minus x squared minus y squared is equal to 5, which means that 4 minus x squared minus y squared is equal to 25, which means that 4 is equal to 25 plus x squared plus y squared. Now, this is impossible, right? X squared plus y squared, the smallest that can possibly be is 0. And so this can never happen. This equation can never be satisfied. Is that horrible? Does that mean that f is bad? Does that mean that something's wrong? No, of course not. Think about what it is you're saying here. You're asking whether or not the graph of the function f intersects the plane z is equal to 5. This tells you that it doesn't. Okay, so that plane is too high. It is above this. And I'm sure that you can quickly figure out what is the highest plane that intersects the graph of this. So what does this thing look like? So we are looking at the graph of f of xy, which is square root of 4 minus x squared minus y squared. Okay, so we're looking at the graph of this thing. And so what is this, just based on what I've said here? So in the YZ plane, it looks like an upper semicircle of radius 2. In the XZ plane, it looks like an upper semicircle of radius 2. In the XY plane, it looks like a circle of radius 2. In the plane Z equals 1, it looks like a circle of radius root 3. As it gets higher, the radius of this circle is decreasing from 2 to root 3 to 1 eventually, all the way until it touches the graph of this at a single point, and then it stops touching it altogether. What does this look like? Okay, so here's X, here's Y, here's Z. So as we saw in the YZ plane, it looks like upper semicircle here. Maybe I'll draw the negatives of these axes. Okay, so in the YZ plane, it looks like upper semicircle of radius 2. In the XZ plane, it looks like the upper semicircle of radius 2. In the XY plane, it looks like a circle of radius 2. And in any plane that actually touches it, the curve I get here are smaller and smaller circles. What is this? Okay, it's kind of not a great picture there because everything's not equal, but this is the upper hemisphere of radius 2. Okay. All right. So this is the upper hemisphere of radius 2. That's the deal. Okay. We could have cheated and seen this. How? How could we have cheated? Remember, f of xy is determining my z value, right? And this, you can see clearly, unlike the previous example where no matter how high my planes went, they were going to intersect the graph of this function because the radius, the radii of all those circles was getting bigger and bigger. Here, of course, past a certain point, some plane z is equal to 10, right, doesn't intersect the graph of this thing anymore. So we could have cheated by noticing that this is the same as the equation z is equal to square root of 4 minus x squared minus y squared. The fact that we're defining z to be the positive root here means that z can only be positive, so there's no negative values here. Okay, so once you're specifying that, now we square both sides. Squaring both sides, I get z squared is equal to 4 minus x squared minus y squared. Adding x squared and y squared to both sides, what do I get? I get the equation for the sphere of radius 2. Now again, you're going to look at this and say, wait, this is the equation for the sphere of radius 2, but you only got the upper hemisphere of radius 2. Why? Because before I was able to do this, I noted that I had defined z to only be the positive values of the square root. Okay, so that's why I only get the upper half. Okay, all right. Let's do one more example. So let's do f of xy is equal to y squared minus x squared. Okay. So quickly, same exact intuition as last time. We want to see what this thing looks like in the plane x, or in the, let's say, xz plane. Okay. So in the xz plane, what does this thing look like? So in the xz plane, y is equal to 0. And so this looks like f of x0, which is minus x squared. So in the xz plane, this looks like a familiar parabola minus x squared. Right? There's minus x squared. In the YZ plane, okay, what does this look like? So this is where x is equal to 0. So f of 0y is equal to y squared. So it looks like another parabola that we like. It's just y squared. So what is this thing going to look like? Right. What do the level curves look like, right? What are the level curves? So level curves, of course, this is setting f of xy equal to a constant. The level curves look like c is equal to y squared minus x squared. What do those curves look like? Well, I won't spoil the fun. Dylan, do multivariate functions have to pass some sort of vertical line test? Yes, absolutely. Absolutely, they do. So, and all of these do, of course, right? So if you check this function, draw a vertical line in space, does it pass through this graph in exactly one point anywhere? Yes, right, it does. So anywhere, if you let that vertical line pass through any point in the domain, of course, you can see the domain here, right, down below. This is the domain, that shaded region. So let any vertical line through space pass through a point in that domain. Does it intersect the graph of the function in exactly one place? Yes. Okay, it does. And that has to be the case. This is what I said last time when I said the rule has to assign values in a way that it assigns exactly one value to every point in the domain. So when you come to a point in the domain, that point doesn't get assigned to multiple values. Okay, there can't be a choice. Okay, there can only be one option. So remember, a helix is not a multivariable function. A helix is not a multivariate function. A helix, that was a parametric curve. That was a function of a single variable that was a vector-valued function, which is a different object, right? When you plug in xy into f, you get a real number, right? But a helix doesn't take in two real numbers. It takes in one real number and spits out a vector, right? But these are not vector valued functions. These are real valued functions. So a multivariable function is, in this course, like when we talk about f of xy, f of xyz, they spit out real numbers, not vectors. Yeah. We'll talk about the thing that you're addressing, we'll talk about later. This comes up when we have to talk about parametric surfaces. Okay, so not to spoil the fun here, what does this thing actually look like? Well, it looks like this. I'm going to go ahead and sketch what it looks like. So imagine what this has to look like. So in the xz plane, it has to look like this downward parabola, but in the yz plane, it has to look like this upward parabola. How does this look? It looks like this. Okay. It looks like a saddle or what is called a hyperboloid. Okay. So, why does it look like this? Here's the origin. Okay. Notice in the YZ plane, which is like this paper, what does this thing look like? What does the cross section of the YZ plane, which is like this paper cutting straight down through this figure, look like? Oh, look, it's a parabola, right? It's the upward opening parabola y squared, right? Now, it's hard to see from this angle, but what does it look like the xz plane cutting down through like this? It looks like this. It's a downward opening parabola in the xz plane. Okay, so I wanted to show you all an example of the graph of a function like this that the cross-sectional graphs looked different, right? Looked totally different. They weren't just copies of the same thing. Because in the previous two examples, both the xy and xz graphs looked identical. Okay, I just wanted to show you an example of this. This is also a very, very important example because this is going to come up later when we're talking about this stuff. Okay, so there's a whole list of some of the basic types of graphs that you can see for some of the basic functions. Obviously, you can't extensively catalog, or you can't exhaustively catalog this stuff because, you know, I mean, there's too many functions, right? But there's a nice smattering, a nice sampling of some of these that I'm not going to draw because my drawings would be terrible. But I will post some of those pages from the textbook later in an announcement. I'll post some nice examples of those things. Okay, so that is kind of the conceptual underpinning. Now we want to talk about actually computing with these things. And so algebraically, right, like if I give you some f of xy is equal to whatever, right? Like assuming that you have already worked out the domain and stuff. If I give you f of xy is the natural log of x squared plus y squared, whatever, you don't have to worry too much about what that thing looks like for now. Let's just say that you want to do some computations with this. Okay, so then, you know, what about operations you want to do? So let's say I have a function g of xy, which is like, you know, square root of 4 minus x squared minus y squared, as we saw before, right? Then things like f plus or minus g, we can make sense of those in a pointwise fashion, just like we always did. This is just literally the sum of these things, right? Pointwise. Okay. Okay. So I can, of course, discuss things like the product of f and g, right? So f times g of xy, what is that? That's literally just the product, right? So it's square root of 4 minus x squared minus y squared times ln of x squared plus y squared, right? This is not under the radical, right? This is just multiplied by things like f over g of xy. I can define in the exact same way in a pointwise fashion. Of course, it might happen that forming a ratio of two functions like this leads to a function that has some discontinuities or some naughty points, right? But we'll worry about that in a bit. So, you know, this would be ln of x squared plus y squared over square root of 4 minus x squared minus y squared. So algebraically, you understand that these operations are defined in the exact same pointwise fashion that they're defined for just usual functions. Okay. All right. So that's that. Okay. So then the better question is all this basic algebra stuff. We don't have an issue with this. So we understand we can just do this all pointwise, just like we did for functions of a single variable, and there's little confusion. So then I want to do calculus, right? This algebra is fine here, but I want to do calculus on these functions. How do I go about that? Well, to do calculus, I need a notion of limit, right? Why do I need a notion of limit? Because if I want to define a notion of derivative, right? Which is kind of the thing that tells me I'm doing calculus. If I wanted to find a notion of derivative, I need a notion of limit because derivatives are defined in terms of limits. So I need to develop the notion of a limit for f of xy. And for functions of 3 and more variables, but it works in the exact same way once you've seen how this goes. Okay, so how do I do this? How do I make sense of this? Well, as I said, you're going to get sick of this comparison. I'll change today's discussion in the today's discussion will actually be like what I've written. Sorry, today's discussion. I didn't mean discussion. I meant description. So the description in the video, I said that we would get to. We might actually still get to it, so maybe I won't change it. Yeah, I realize now we still have like 20 minutes, so maybe we'll actually still get to it. So in Calc 1 world, let me draw a picture of function. So maybe function looks like that. Now, if I give you that function, right, here's my function f. If I give you this function drawn like that and ask you, is that function continuous on all of its domain, which here I'm specifying to be like a to b, right? Is that function continuous on all of a to b? You would look at that and you'd say yes. Right, it is. And intuitively, maybe you would say, oh, well, the reason why this function is continuous is that I drew the graph of the function with a pen, and to draw the graph of this function, it was sufficient to put the pen down, draw, and never lift the pen from the paper, right? And intuitively, that is what the graph of a continuous function should be. It should be something you can draw by putting pen down, drawing, and never lifting the pen. Okay. All right. Intuitively, that's kind of what you understand about the graph of a continuous function. There's no gaps, no holes. Right. And so this would be a perfect example of a continuous function. But you might recall that depending on how exactly you learned this, you may have been told the epsilon delta definition of continuity. I'm not going to state that rigorously or anything. All I'm going to say is, what is the idea behind a function being continuous at a point? And continuity is defined point-wise. So we talk about a function being continuous at a point, and then if a function is continuous at every point in its domain or on some set, then we say it's continuous on that set, meaning it's continuous at every single point indicated in that set. And so, like here, what does it mean for a function to be continuous at some x naught, okay, in its domain? What that means is that if you specify, right, a window, right, an error tolerance window, okay, if you specify a window, and this window can be as narrow as you like, okay, it could be as fat as you like as well, but you know, the point here is we're wanting to make this window as small as possible. We're trying to be as accurate as possible, so we're trying to make this window small. So the idea is that you specify an error tolerance, okay? So you specify an error tolerance. So here's your error tolerance window, okay? So once you've specified the radius of this window, right, in your range, if my function is continuous, it means that I can always find some positive real number that is the radius of some window down below that matches this error tolerance window up above. Meaning that it sends this entire little interval, which can be really, really, really small, about x naught, to be entirely contained in this error tolerance window up above. So again, just to go through it, you specify some error tolerance Okay, and no matter how small you make it, I can always find a window of values around this point that get squeezed into that error tolerance window. What is this saying conceptually? It's saying that the functional value, right, near x naught is arbitrarily close to this value you're saying that, is the functional value of f. And so this is saying that the function f is continuous at x naught. Okay, and you might remember some things like one-sided limits. One-sided limits were this picture, except you only considered one side of this interval at a time. The main strength of continuity is that all values on both sides of this x naught are being considered simultaneously. Okay, so I'll come back to that in a second. So that's continuity in Calc 1 world. Okay, so continuity in Calc 3 world aims to mimic this exactly. Okay, but what do I have to do to make sure that I nail down all of the important stuff? Well, the graph of my function, right, maybe it looks something like this. Okay, so here's my f of xy. Now I have, rather than having a 1D interval as my domain, I have some two-dimensional region, R is my domain, right? You can think of it as if I take a flashlight and I'm shining it straight down on this object sitting in space. This is the shadow cast on the xy plane by doing that. Okay. Now, if I want to talk about continuity at a point x naught, y naught, okay, then what happens here is I want to try to mimic exactly what happened in the Calc 1 case in this setting. Okay. So then the idea is that I have some error tolerance window up above that I specify. Okay. And what I want to say is that I can squeeze all values near x naught, y naught into that specified window, just like I did here. Okay. But here, the values near x naught, this is a 1D thing. It's an interval, right? So when I say values near x naught, I'm talking about values in some real interval about x naught. Here, my domain is two-dimensional. So when I talk about points near x naught, y naught, it's not some interval. It's actually points in some disk centered at x naught, y naught. So I am allowed to take all points near x naught, y naught in this sense and say that those points are squeezed into this error tolerance window up above if f is continuous at x naught, y naught. Okay. Now that might make it seem like continuity is stronger, okay, in this case, like it's a harder condition to satisfy, but it's not really. It's just that there wasn't enough room to move around here. So to give you an example, right, of this can be really confusing. Here, right, one of the facts you learned in Calc 1 was that if you considered a function and you considered its one-sided limits, right, so its limit from the left and limit from the right at some point, then a function was continuous at a point if and only if both of the left and right-sided limits existed and were equal to each other, right? This was one of the key things you did early on in continuity. When you were trying to show that a function was maybe discontinuous at a point, you would show that, when I approach it from the left, I get this limit, and when I approach it from the right, I get this other limit that's different, and those need to match up if that thing is going to be continuous. And approaching from the left or right, if you're approaching from the right, you're picking in values here. If you're approaching from the left, you're picking values here. Okay, it's simple enough to explain. In Calc 3, though, this same thing, what is the notion of a left and right side limit? There's not really one that carries over exactly. Instead, I have to be allowed to approach from any path that I want to. Any curve you like that passes through this point, I can approach this point x naught from any path. Okay. Now that definitely makes it seem like continuity here is stronger, because look at you can imagine some crazy path, right, that you can use to approach some point x naught y naught, and what you say about a function being continuous at the point has to work for a limit taken along that path, right? And it has to work for every limit taken along every path. Definitely seems like a stronger condition. It's not, though. You're being fooled by the fact that in Calc 1 you had so little room here that every path is just this line, right? It's just going to be some piece of this line, right? Because there's only one dimension. It's not a whole lot of room to work with. Okay, so actually it's the exact same condition. It's not any stronger in one setting or the other. Okay, it's actually the same thing. This leads to some examples of functions that are discontinuous in a funny way. So I'll give an example. I'll give a quick example of how this works. That kind of is the key thing. So what is the main fact? So main fact. Limits behave in similar ways with only slight differences. When I say similar ways, I mean similar ways to what you're used to from Calc 1. So I'm going to do a single example of a function not having a limit at some point. So let f of xy be the function y squared minus x squared over x squared plus y squared. Okay. I want to compute the limit as xy approaches 0, 0 of f of xy. Okay. So this will be good practice to show you the algebra that's involved in these limits, and then we will promptly never use them again, really. This is just the stuff that's underpinning what's going on here. So if I try to compute this, okay, what's my idea here? So my idea is approach with different paths. So approach 0, 0 via different paths. So what's the idea? What does the graph of this thing look like? I don't know. It looks weird. Okay, the graph of this thing looks weird. I'm not going to attempt to draw it. But the idea is that whatever the graph of that thing looks like, here's the xy plane down below. The graph of this function lies above the xy plane. And I want to compute the limit of this function as points approach 0, 0, the origin. And I'm allowed to approach it from any path I want. Okay. Well, let's do a couple of things here. Let's, what if I approach this via the positive y-axis? So what if I approach it like that? So on the positive y-axis, x is 0, right? So if x is 0 and y is positive, and y is going to 0, then what is the limit as xy approaches 0, 0 along this path of f of xy? Well, along this path, x is 0. So this is y squared minus 0 squared over 0 squared plus y squared, which is y squared over y squared. Since y is always positive here, we're just approaching 0, so there's no 0 in the denominator here. This is 1. Right? You'd have to be careful if y was allowed to be 0 here. It wouldn't necessarily be 1. Okay. All right. But what if I approach from the positive x-axis? Right? So here, y is equal to 0, x is positive, and x goes towards 0. What is the limit as xy approaches 0, 0 of f of xy? Well, this is going to be 0 squared minus x squared over x squared plus 0 squared, which is going to be minus x squared over x squared. Again, x is positive, it's just going towards 0, so this is minus 1. So approaching from my first path, I get a limit of 1. Approaching from my second path, I get a limit of minus 1. But for this thing to be continuous at this point, these would have to agree. It would have to agree not just for these two paths, but any paths I picked. Okay, and so this limit does not exist. Okay, D and E, this limit does not exist. All right, this is a canonical example of a limit doesn't exist in this way. So this just shows you kind of sort of the things that can go wrong with continuity. But for us, the definition of continuity is going to be exactly the same as it was for Calc 1, and that is, so my definition is f xy is continuous at a point x naught y naught in its domain if the limit as xy approaches x naught y naught of f of xy is equal to f of x naught y naught. This was exactly what you said in Calc 1. There's many equivalent ways to characterize this. One is to say that this limit can be computed by just evaluating f at the point x naught y naught. Another way of saying it is that you can pull the limit through f. Continuous functions are precisely those functions that you can factor limits through. Okay, we say that f is continuous on R if it is individually continuous at every single point of R. At every point x naught y naught in R. Okay. Okay. So with a notion of limits and continuity, we can now define derivatives of f of xy and f of xyz and so on. Okay. And so that's what we'll do next time. So beginning next time, I will start with the definition of taking derivatives of these things, and then we will quickly progress through this chapter 13 material, because basically once you have the computational tools at your disposal, it's very, very easy to set up all of the stuff that comes next. So we'll progress through chapter 13 pretty quickly because of that. Once I write down what I write down in the next lecture, it won't take long to blaze through the rest of chapter 13, which will take us through, if you're following the Calc 1 curriculum, it takes you through the our equivalent of the first and second derivative tests. Okay, so that's the plan. So anyway, I will see you all on Friday. So you have discussion tomorrow where your TAs will go over solutions to the exam. Okay. All right. So I will see you all Friday.